Welcome students. This is the fourth session in Control Systems Engineering. In the previous session, we saw transient responses and the types of responses that we got in first order systems and in second order systems. In this particular session, we will be looking at steady state errors and Routh criteria. Now, as I described in the previous session, there are two response types. First is transient response and the second one is steady state response of any output. When there is a steady state response, there is always some error, and this error is known as steady state error. We are interested in finding what kind of errors that we get with different kind of systems. Further, we will see what is the notion of stability, and we will be introduced to one of the methods to find out the stability of the system. Let us look in detail how are we going to study in this chapter. The first topic that we will be covering is the transfer function poles and zeros. As I mentioned, we will be interested in the types and kinds of systems in which different types of steady state errors occur, and that's why it is important to understand the transfer function poles and zeros, or the definition of the terms poles and zeros characteristic equation. Next up, we will see what is meant by type and order of the system. As I already mentioned, there are different types and kinds of system. So learning about types and order of the system will help us understand the steady state errors in a better way. In the third topic, we will be introduced in steady state error. So we will study in detail how exactly an error occurs and what are different errors generalized for different types of systems. Finishing the third topic, we will move on to the notion of stability. We will see the different definitions of stability or the different perspectives of stability. After completing the fourth topic, we will move into Routh criteria. It is one of the methods to find out the stability of the system. So let us start with the transfer function poles and zeros. Transfer function poles and zeros. In this session, we will see what is meant by transfer function polynomial, what is the meaning of poles and zeros. Let us go forward and see what is a transfer function polynomial. Let us look at this particular term, g of s. G of s is given as k into s minus capital A into s minus capital B into s minus capital C and so on, divided by s minus small a, s minus small b and s minus small c and so on. As you can see, the transfer function g of s is represented as certain eigenvalue k into some numerator and divided by some denominator. So the form of transfer function here is of a fraction, and this very fraction is known as a transfer function polynomial. Now the denominator of this transfer function is known as characteristic equation. Now the roots of numerator, which are capital A, capital B, capital C and so on, are known as zeros of the transfer function, because putting s equal to capital A or capital B or capital C and so on will give value of g of s to be 0, and hence these these values of S or the values of the frequencies which take up at S are known as zeros. Similarly, the small a, small b, small c, so on are those frequencies where transfer function is undefined, and hence the small values or the letter small a, small b, small c for S in this case are known as poles of the transfer function. The poles and zeros characterize the system for its stability, which we are going to study in the later slides. I hope you have understood what are transfer function poles and what are transfer function zeros. Let us go forward and see what is meant by type and order of the system. Type and order of the system are also kinds of system classified according to the characteristic equation of a transfer function. Let us see order of the system and the definition of type of the system. As you can see on the left hand side, g of s is a transfer function wherein there is gain k in the numerator and the denominator is characterized as s raised to small n into 1 plus st. Now, such a system in which there are n number of poles at s equal to 0. So at s equal to 0 you have n values, and hence small n is the type of system which are nothing but number of poles at s equal to 0. So if I have a system such as 10 upon s raised to 3 into 1 plus 5s. So the type of system for this g of s would be 3. Similarly, we saw in the previous session for a first order system such as a heater, it was modeled as k upon 1 plus st. Here, number of poles at s is equal to 0 are 0, and hence type of such system is type is equal to 0. At max, in the control system syllabus that we are going to deal with, we will be dealing with type 0, type 1, type 2 systems. Sometimes you might encounter a problem with type 3, 4 and so on, but in such cases that problem will be simplified according to the mathematical rules and which will be easy to solve. So I hope the definition of type of a system is clear. Type of system is nothing but the number of poles of a transfer function at s is equal to 0. Let us go forward and check what is the order of the system. So the order of the system is nothing but the highest power of s or the highest exponent of s that is occurring in the characteristic equation of the transfer function. As you can see in this particular example, g of s is given by k divided by s raised to n into 1 plus st1 into 1 plus st2 and so on till 1 plus stm. Now, if you multiply this s raised to n to each of these values, whatever equation that you will get or whatever polynomial that you will get in the denominator will have its highest power as s raised to n plus in index m. So means highest power will be s raised to n into s raised to m, because all these s will be multiplied at a certain point and you have m such values of s. So highest power with certain coefficient you will get ck, which would be the coefficient of these values. So the highest term will be ck into s raised to m plus n, and this will be the highest exponent in the characteristic equation. So the order of the system will be m plus n. So for any system, for any given system g of s, let it be like 10 upon s raised to 3 plus 1 plus 5s into 1 plus 2s. What is the order for this particular system? The order will be s raised to 3 into s into s, which is s square, and s raised to 5. So highest exponent that is occurring in this particular characteristic equation is 5, and hence the order of the system is 5 in this case. At the same time, type of the system is nothing but 3. So try to find out the type of the system and order of the system. This will be the initial exercise for all the systems that you encounter. Once you are able to find out the type and order of the system, it will be easy to go into the notion of stability and can calculate the steady state errors. Let us go to the next slide and see what are steady state errors. In steady state errors, we are interested in finding out the final value of the system response. Once we are able to find out the final value of steady state or final value of a system response, we will compare the final value of the system to the reference value or the expected value that we are desired in, and we will find out the error signal. This very error signal will give us the steady state error. Steady state error is significantly important in the control systems as systems are becoming more and more accurate and more robust. To make system ideally or to make system close to practical systems, it is very important to make the system with zero errors or no errors at all. But still, we have to find out in what tolerance band can we allow the error to occur. And this is how we will save a lot of cost not doing 100% accuracy. That is why we need to study steady state errors and how these steady state errors occur in different types of systems. For type 0 system, there is a general type of steady state error that you get. For type 2 or type 1 system, there are different steady state errors that you get for different inputs. Later on in this chapter, we will be studying steady state errors versus type of system. Different types of systems will be subjected to different inputs, and we will calculate the steady state error for the system. Now let us go forward to the next slide and see what is a final value theorem. As I described, for any system, let us say system A, if you apply a step input u of t and you get output y of t. If you plot a graph of y of t, you will get certain graph like this. Now, let us assume this A is first order system so that you can connect to this particular graph. This is the first order response for step input and this is the value 1. Now, as you can see, the error at the starting of the response at t equal to 0 is very large, is 100% error. But as time passes by, as time goes forward, the error becomes less, and in the tolerance band of 3% to 5%, we allow the error to occur. Now let us assume for time at t equal to infinity, our value will virtually be equal to 1. That means our error will be 0. This is the same statement which is used in final value theorem. According to final value theorem, the final value of any system f of t or any function f of t is found by taking limit of that function for t tending to infinity, which is a very simple statement to understand. What do you do to find out the final value of a system? Just put t equal to infinity. Now this very statement translates into Laplace transform as limit s tending to 0 s into f of s. The proof of the system is not important at this particular time. You will be studying the proof of this statement in different subjects such as signal systems and all. Let us assume that we have this proof and we will use this particular statement as a final value theorem to calculate steady state errors. So just remember, final value theorem says a final value of any system can be determined by taking limit s tending to 0 for s into f of s. Now we will go forward and check what is an error signal. Let us complete this figure. This is our particular block diagram in which, as you can see, we have given the input r of s and a feedback is coming from the output y of s getting multiplied by h of s and is subtracted from the reference signal r of s, which ultimately generates an error signal e of s, and this error signal is fed to the controller block or say the gain of the system, and according to this error signal we get the output of the system. To translate these into mathematics, we can use following equation. E is equal to r minus hy. E is equal to r minus h into y. So this is right. Now our aim is to find out E of s. So we will have to eliminate y from the system. Now we know y is also is equal to E of s into g of s. So replacing y by E into g, we get E is equal to r minus h into Eg. So this is the equation which is formed by equation 1 and equation 2. From using equation 1 and 2, we get this particular equation. Rearranging this equation and taking out E common in the left side, we get E into 1 plus gh is equal to r. Solving it completely, we will get this particular value. E of s is equal to r of s upon 1 plus g of s h of s. Now look carefully. We have steady state error is equal to ESS is equal to limit s tends to 0 for s into E of s. So our error signal is nothing but r of s upon 1 plus g of s into h of s. This r of s is whatever input that we wish to apply to a system. This r of s could be delta function, could be u of t, could be r of t, could be s of t or parabolic function. So taking its Laplace transform, it will be either 1, it will be either 1 by s, it might be either 1 upon s square, or even 1 upon s cube, depending upon the type of input that we are applying to the system. G of s, h of s is nothing but the closed loop transfer function. So just imagine h of s is equal to 1. So if h of s is equal to 1, we just have g of s in the denominator, and g of s is nothing but the open loop transfer function of the system. So ignoring this feedback, if this is 1, we'll just have g of s going from e of s to y of s. So g of s is nothing but open loop block or open loop transfer function. So for e of s, what are the inputs that we need? We need some reference input, and we have to know the value of g of s, which is nothing but the open loop transfer function. Once we know r of s and g of s, we can calculate ESS or the steady state error. Let me write steady state error to be is equal to limit s tends to 0 s into e of s. So ESS is nothing but s into r of s upon 1 plus g of s h of s. You will be given the value of h of s into g of s, or only the value of g of s, and it will be mentioned that the value of h of s is unity. So you will be able to find out the steady state error. Now let us find out, or let us take an example. Let us take an example of such a system. Let us take g of s to be is equal to 1 upon s into 1 plus 10s. So this is my g of s. Let h of s is equal to 1, and let us say r of s is equal to 1 by s. That is, we have step input. Now I am interested in calculating the steady state error for the system 1 upon s into 1 plus 10s for step input. Let us calculate what is E of s. E of s is nothing but r of s upon 1 plus g of s into h of s, which gives me 1 by s upon 1 plus 1 upon s into 1 plus 10s. So this is my E of s. My steady state error ESS is equal to s tends to 0 limit s into E of s, which is nothing but 1 by s upon 1 plus 1 upon s into 1 plus ns. So this is how you can find out the steady state error. Now in the numerator, as you can see, s into 1 by s will be 1. So this would be 1 upon s into 1 plus 10s plus 1, and numerator you will get 1 plus 10s into s. Now calculating this particular value for limit s tending to 0, we will get, if you put s is equal to 0 now, sorry, we will get ESS is equal to 0. So in this particular problem, our steady state error is 0. So for a type 1 system and the step input, you get steady state error to be 0. This is just an example, and we will be seeing a particular steady state error versus type of system table in the next slide. So this is the type of system versus ESS, or the steady state error table, in which on the left hand side first column you see different inputs named as step input, ramp input, parabolic input, and then you have types of systems in the first row, which is type 0, type 1 and type 2. So we have for type 0 and for the step input 1 by s, you get steady state error in the form of k upon 1 plus kp. As in the previous example, we also saw for type 1 system and the step input, you get steady state error is equal to 0. Let us try and calculate the steady state error for type 0 and step input. So for a type 0 system, let us say my type 0 system g of s is equal to k upon 1 plus 3s. Okay, so let this be my type 0 system, and my r of s is nothing but 1 upon s. Now I am interested in calculating the value of steady state error. So ESS is nothing but s into r of s upon 1 plus g of s h of s. I am assuming h of s to be unity. So s into r of s would be equal to 1, and I will get 1 plus, sorry, let me use the eraser. So I will have 1 plus k upon 1 plus 3s. Now, as I can see, putting s is equal to 0 in this particular function, without any doubt I can put s is equal to 0. So I get the function in the form 1 plus 1 upon 1 plus k by 1, which is nothing but of the form k upon 1 plus kp. So this is how you can get the steady state error. Okay, so this kp is known as proportional constant. Often in the different problems, you are expected to calculate this constant kp. So problem might come where you are given r of s, g of s, and you are required to find out the proportional constant. So you will be expected to calculate the steady state error first, convert the steady state error form in the form of k upon 1 plus kp, and whatever is the value of kp, you will get it as a proportional constant. Often this k will be equal to 1, and hence kp will be of form 1 upon 1 plus kp. You will be expected to find out this kp. Now let us go forward and just revise this table. I will erase everything for you. Thank you. So as we saw, for type 0 system and step input, you get the value as k upon 1 plus kp. Then for type 1 system and for the step input, you get steady state error to be 0, and similarly for type 2 system, you get steady state error to be 0 for step input. Also, ramp input generates infinity steady state error for type 0 system, but at the same time ramp input gives us a finite steady state value error for type 1 system. Parabolic system gives us finite steady state error value for type 2 system. The constant kv is known as velocity constant. As I described, often it is required to find out in problems the proportional constant, velocity constant. Also, this K is known as acceleration constant. Let us get into a trick to understand this table. Just assume the step input to be coded as 0, ramp input to be coded as 1, and parabolic input to be coded as 2. Now, we will call the step input to be is equal to 0, ramp input to be equal to 1, parabolic input to be equal to 2. When the type of the system and the type of input are of same value, then you get the finite value for steady state error. Understood? So basically, you have type compared to the input type. Okay? So type is compared to the input. If both are equal, you get finite steady state error. Okay? For type greater than the input, okay? So if type is greater than input, you get 0 is equal to ESS. Okay? Understood? When type is greater than the input, you get 0 as ESS. Look at this type. Type is 1 and input is 0. You get 0. Also, for type to be less than input, you get ESS is equal to infinity. Okay? So this is how, by understanding and looking at this particular table, you can easily remember types of ESS or the steady state errors that you get for different types of inputs. Often in control systems engineering, you will be encountering type 2 systems at max and will be subjected to the complicated inputs such as parabolic input in very rare cases. Most of the times the inputs are step, ramp and rarely parabolic system. So let us go forward and see the stability concept now. We will be seeing different definitions of stability, or rather different perspectives of stability. How exactly we can define stability? So let us understand stability is nothing but the undesired value of any function. And undesirable means the value is subjective. It depends upon person to person. What I desire is not what you desire. And that is exactly why stability is different in different perspectives. Okay. So if you have a system A, okay, and if you have different inputs such as A, such as B, and if you have multiple outputs such as X1, X2, X3, X4, and if my desired output is X4, okay, and if I am happy with whatever output I am getting, this system delta, or say this particular sigma system, is stable for me. Okay, if I am interested in output X4, for me the system will be stable. But for you, if you are interested in output X1 and this output X1 is not how you liked it, or this X1 is not how you wanted it to be, so this very system will be unstable for you. So a system stability depends upon the user. So when we define what output we want and what input we want, then only we can define the stability. So whenever there is a question of stability, you must identify what is the output and what is the input. Most of the times in problems, it is mentioned what is output and what is input. But in depth, it is necessary for you to understand that for a very single system or for same system, there might be different outputs and different notions of stability. Let us see in detail what does stability mean. So stability is nothing but small changes in input that do not affect large changes in output. So stability is, so if we are talking about stability, for a small change in any input R of t, and if I have output y of t for system A, if I change R of t to be plus delta R, my y of t should not increase to infinity or a very large value. So this is one of the notions of stability. So small changes in input should not affect large changes on the response. That is one of the perspective of stability. In the second statement, you can see, in case of stability analysis, response and stimulus are subjective terms, as I explained just earlier. What is BIBO stability? BIBO stands for bounded input, bounded output. So BIBO means BIBO stability exists if bounded stimulus produces bounded response. Now what is known as bounded? Bounded is nothing but the integration of that particular signal from minus infinity to infinity. Let us say that signal is f of t. Taking mod of that signal, dt is less than infinity, or that is finite. Such signals are known as bounded signals. Let us take an example of signal e raised to at. Okay, the graph of this particular function is like this. If you try and calculate minus infinity to infinity, the area under the curve for e raised to at, it will give infinite, and hence this particular input is not bounded. Okay. At the same time, if you take signal e raised to minus at, which is of the form this, which is a decaying signal, and the area under the curve from minus infinity to infinity is finite. Okay, and that is why e raised to minus at is a bounded signal. Okay, so this is how you define bounded signals. And if I am inputting bounded signal to a system, I expect my output to be bounded. Bounded input to a system A. If it generates bounded output, okay, then my system is known as BIBO stable. Okay, so this is one of the definitions of stability. We'll be encountering BIBO stability or a lot of stability analysis into bounded input and bounded output. There are different notions of stability. As we saw e raised to at and e raised to minus at, we saw e raised to at is a stable signal and e raised to minus at is a stable signal. If we take a Laplace transform of these signals, we get 1 plus s minus a, and at the same time for this particular signal we get 1 upon s plus a. So as you can see, if the root of this particular characteristic equation is positive, if s minus a is, the root is s is equal to a, and for a greater than 0, this is a positive root, and hence for positive roots in S plane, okay, so this is sigma, this is j omega. For any root s is equal to a, the system will be unstable. Any roots which occur in the right hand side of S plane will be called unstable. At the same time, every root that is occurring in the left hand side of S plane, for this particular system, S is equal to minus a, and hence the root is lying on the left hand side of S plane. Hence we can see this system wherein the roots lie on the left hand side of S plane are stable. The roots which lie on the imaginary axis, say here or here, are known as marginally stable. This is written on this slide. All roots of characteristic equation must lie on left hand side of S plane for stability, as I described, and non-repeated poles on imaginary axis makes a system marginally stable, because these systems are very close to stability and also instability. So whatever roots are there occurring, so for this you have stable system. For the right hand side roots you have unstable system, and for the roots occurring on the imaginary axis you get marginally stable system. Okay, now let us see the graphical representation of location of poles and zeros and stability, and then go forward and see the Routh criteria. Routh criteria is developed according to the very rule that we studied just now. We will see what Routh criteria is. First, let us look at the location of poles and the stability notion. As I just mentioned, if you have a transfer function 1 upon s plus 1, you have root on the left hand side or the pole on the left hand side of S plane, and the system response is e raised to minus t, and response curve is shown, which is decaying, is stable, because this is a bounded response. Okay. Similarly, if you take the root at origin, okay, you have a transfer function 1 upon s. This is the system response is equal to 1, and response curve is given by this particular state, this particular amount. Okay, but the value of this particular integral for this particular system 1 into dt depends upon the limits of this function and not on the function of the system, because if my limits are finite, I'll get finite response. Okay, and because my limits are infinite, I'll be getting infinite response. And this is exactly why this particular response is categorized as marginally stable response. As we already mentioned, the location of pole on the right hand side of S plane with the transfer function 1 upon s minus 1 will give me the system response as e raised to t, as you can see here. I think if it is not visible, I'll write e raised to t, which is giving me the response curve as this, which is continuously increasing, which is unstable because the integration from minus infinity to infinity, e raised to t, e raised to t dt will give me infinite value. As you can see, even if you stop these limits to go to infinity, still we'll be getting very large value for whatever time limits that we take. In this particular system, you have finite imaginable value. You can easily calculate that, but for such an increasing system, for large values of p, you will get a very large value of e raised to p. And that's why this system is unstable. Let us see what is a Routh criteria. Routh criteria says that for a characteristic equation delta S, that means for any system g of S is equal to k upon delta S, where delta S is nothing but the characteristic equation of g of S. If you have the characteristic polynomial as in the form a naught s raised to n plus a1 s raised to n minus 1 and so on till a of n, then if the signs of the coefficients of all the powers of s are same, then the system is stable. So if the signs of a0, a1, a2 till an is either positive or either negative, you will get a stable system. But if any change is there, let's say if not all the signs are same, maybe a1 is different than a2, then you have to find out the stability by following rule that is mentioned below. Now, the arrangement that you see on the left hand side with different rows and columns is known as a Routh array. We will see how to build a Routh array. Let us focus on the first two rows of the Routh array, wherein you can see a row of n and the row of n minus 1. You write s raised to n and s raised to n minus 1, and we will write down the coefficient of s raised to n, which is a naught, and then write down the alternate coefficients till it gets exhausted. So we have a naught initially, then we will write a2 alternate, and then we write a4 and so on. Now we'll come back to the row of n minus 1. We'll write the coefficient of s raised to n minus 1, which is a1, going alternate again a1, a3, a5, and we'll go till this list exhausts. Now after building up a0, a2, a4, a1, a3, a5 rows, we have to calculate the following rows, which are known as n minus 2 row, n minus 3 rows, and so on. We have to go till the row of 0. Now how to calculate the elements in s raised to n minus 2 row, s raised to n minus 3 row? So it is given as in the right side. B1, which occurs at the first position for n minus 2 row, is calculated as determinant a0, a3, a1, a2. So basically you multiply a1, a2 minus a0, a3. Look at the negative sign here. So if you take determinant and multiply it by negative sign, you will get a1 into a2 minus a0 into a3 divided by a1, and this is how you calculate b1. For b2, the same way you should calculate a1 into a4 minus a5 into a0. As you can see here, I'll write a0 on the places of 1 just for the ease of understanding it. So for b2, you'll have to calculate a1 into a4 minus a5 into a0 divided by a1, as you can see here. Okay, this is how you keep on calculating s raised to n minus 2 row. Then c1 will be is equal to these functions. So b1 into a3, okay, b1 into a3 minus b2 into a1 minus b2 into a1 will give us c1. So you have to use about 2 rows to calculate the determinants and put the negative sign. You will have to calculate the elements till the row 0, and once you get these coefficients as a0, A1, then you get B1, B1, C1 and so on. If till row 0, if you have coefficient K1, we will look at the signs of A0, A1, B1, C1 and K1. And if the signs of A0 to K1 are either positive or either negative, but all signs should be same, then we can say that the system represented by G of S is stable. So this is how Routh ultimately created an array to show how to determine the system stability or instability. Let us take an example of Routh array. We will have a characteristic equation as s raised to 5 plus 15 s raised to 4 plus 185 s cube plus 725 s square minus 326 s plus 120. As you can see, the signs of each coefficient is not same. As you have minus 326, we will have to create a Routh array to check the stability of the system. Now, we will start from s raised to 5 and s raised to 4. First, we will write s raised to 5 and s raised to 4. We will write the first coefficient of s raised to 5 to be 1 and go on writing the alternate coefficients, which are 185 and minus 326. Then you have s raised to 4 and the coefficient is 15. Writing 15, then 725 and then 120. This is how you write down this many elements. Now you have to calculate this particular element. Okay, this can be calculated as 15 into 185, okay, minus 725 into 1 upon 15, which gives me this particular value, 136.7. Also, to calculate this value, for calculating this value, the operation would be 15 into minus 326 minus 120 into 1 upon 15. Okay, so this will give me minus 334. This is how you keep on going and keep on calculating the terms, the rest of the terms, until you get the final value for s raised to 0. You will check the signs of all the terms. As you can see, all signs are positive except for the row s raised to 1, and hence the system is unstable. If signs would have been same, the system would have been stable. Let us see the summary for this session. We saw that the stability is characterized by transfer function poles and zeros. Once you know poles and zeros of the system, you can place the poles in the S-plane and check the stability. Also, once you know the poles, you know the characteristic equation, and then you can calculate the stability using Routh criteria. We also saw that the steady state errors can be easily determined by the knowledge of poles and zeros. By the poles and zeros, you know the type and order of the system, and that's why you can easily calculate the steady state error. Routh criteria is one of the ways to determine the stability of the system. In the next sessions, we will be looking deeper into the ways of calculating stability. Thank you.